All right. So next concept we are having heaps and heap sort. Okay. Next concept is heaps and heap sort. The screen visible? Is my screen visible?
Yes, sir.
Yes, sir.
It's visible.
Okay. Now we'll first learn what is a heap and how to perform heap sort. Okay. Next, how to construct a binary tree. I will see here. What is this says? What is this a heap? So it is a partially ordered data structure that is especially suitable for implementing the priority queues. Okay, it is a partially ordered data structure, right? It is a partially ordered data structure. So it is suitable for implementing these priority queues. Okay. Now what is this heap? So it can be defined as a binary tree. It can be defined as a binary tree with the keys are assigned to its nodes. Binary tree, and this binary tree should be a complete binary tree. Okay, so these keys are assigned to its nodes. Next we'll see how to construct this binary tree and how to perform this heap sort of that particular binary tree. Okay, so if we want to construct a binary tree, we need to follow some set of conditions. What is that condition? The first one, the tree's shape requirement. Okay, the tree's shape requirement, that is, since we are telling it is a binary tree, so it should be a complete. So the binary tree should be a complete, that is, all its levels should be full except the last level where only some rightmost leaves may be missing, right? So you studied what is a binary tree, what is a complete binary tree, right? So here when we are constructing this binary tree, the tree should be a complete binary tree. Next condition. So the parental dominance, that is, already here we studied the keys are assigned for its nodes. The keys are assigned for its nodes. So when a node is created in a binary tree, then the root node we should define, right? Then the root node we should define. That is, the key at each node is greater than or equal to the keys at its children. Kindly remember here the parental dominance, that is when we create here root node. So the key that is taking the root node should be greater than or equals to its children. It should be greater than or equal to its children, that is the root node, right? So this is the parental dominance we are having. So this is one condition we should keep it in our mind. Next, some of the important properties of heap are the height of a complete binary tree with n nodes is equal to log n. Okay, the height of a complete binary tree with n nodes is equal to log n. Next, the root of a heap always contains the largest element. The root of a heap always contains its largest element. Kindly remember, the root node should be greater than its children. Always the root node contains the largest node compared to its children. Next, a node of a heap considered with all its descendants is also a heap. Is also a heap means the subtrees what we are having, the subtrees, it should be also a heap tree, means the node root node should be greater than its children, its descendants. Okay, next, a heap can be implemented as an array by recording its elements in the top down left to right fashion. Okay, so here always the parental node keys will be in the first n by 2 positions of the array, while the leaf nodes or the leaf keys will be in the last n by 2 portion. For example, here you just observe. Let us take, this is a tree we are having. Okay, this is a tree we are having. So here the root nodes are 10 is the root node. Similarly, 5 is the root node. 7 is the root node. Next, 4, 2, 1 are the leaves, right? So 10 is the root node, right? 10 is the root node. What are the leaves we are having for this? Leaves we are having 5 and 7, right? Next you take, so this is finished. Next you take 5. Are we having any leaves for this 5? Yes, sir. So leaves are 4, 2, right? So this 5 is finished. Next you take 7. Are we having any leaf nodes for this 7? Yes, 1 is there, so 1, right? So 7 is finished. You just observe here, the first n by 2 part is acquired by the root nodes. The first n by 2 part is acquired by the root nodes, and the last n by 2 part is acquired by the leaf nodes, right? The first n by 2 part is acquired by the root nodes, and the last n by 2 parts are acquired by the leaf nodes. Always keep it in mind. You just see, so this is the array representation of this particular tree. Array representation of tree. Is it clear? So we will start from root node. We will start from the root node. The first root node is 10. Okay. The first root node is 10. What are the chains for this 10? 5 and 7. So next, so this 10 is finished. Next we will go for 5. So next we will go for 5. What are the chain nodes we are having for 5? 4 and 2. So next we are having 7. What are the chain nodes we are having for 7? 1. Right? So this is the array representation of this particular tree. Is it clear? So that is what we are saying. So the parental node keys will be in the first n by 2 portions or positions of the array, while the leaf keys will be in the last n by 2 positions. Right? So here it is first n by 2, all parent nodes are there. The leaf nodes we are storing in the last n by 2 positions. Okay, so here you should keep it in mind. First one, always the root node should be greater than the leaf nodes, right? The root node should be always greater than the root node. Second point, we should keep it in mind, the subtree. Okay, the subtree should also be a heap tree. Okay, the subtree should also be a heap tree. So these points you should keep it in mind. Heap tree means again subtree. In the subtree, root node should be greater than its child nodes. Okay, then we can say that it is a heap tree. Is it clear? Is it clear? Kindly respond, please. Okay. Is there any doubt?
No, sir.
No, sir.
Okay. Now we will take an example and we will see how to construct a heap tree, right? Okay. So before that, we will see the different types we are having to construct a heap tree. So there are two types. Okay, there are two types we can construct a heap tree from the given keys. One is bottom up heap construction, the other one is top down heap construction. Okay, one is bottom up heap construction, other one is top down heap construction. So these are the two alternatives, these are the two types we are having to construct a heap for a given list of keys. For a given list of keys. So the first one, let us take a first one, bottom up heap construction. Bottom up heap construction. Okay. First we will take an example, later we will go with this theory part so that you can understand well. So let us consider one example. So first step, the list of keys are given. Okay, the list of keys are given. The list of keys are given. So our first step is you construct a tree for this keys. Later we will go for heapifying. Okay, later we will go for heapifying the tree. Okay, so what is the first step says? First step is construct a tree for this given list of keys. So take a two just to see how we are constructing. Since it is a complete binary tree, so kindly remember we will go to construct like this. First root node, then left, then right? Root node, left, right. So it is complete now. Again, we will start from here. So next element, next element, next element, next element. Again, if there is any element, then we will go like this. So we will construct a tree like this. Is it clear? Okay, right? So always keep in mind first element, second element, third element, fourth element, fifth element, sixth element, seventh element, 8, 9, 10, 11, 12, 13. If you are having 13, we will stop here. If you are having 14, 14, we will stop here. Is it clear? This is how we will construct a tree. Okay? Is it clear? Kindly respond, please. Okay, so now we'll go to construct a tree. So first we are having a 2. Okay, first we are having a 2, next 9, next 7, next 6, next 5, next 8. So tree construction is finished. Once the tree construction is finished, then we will check for parental dominance. Parental dominance, what is it says? Always the root node should be greater than the child node. You just observe here from 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 the last leaf node we will check. Okay, from the last leaf node we will check. Kindly observe here. Let me take. I will take another one. Okay. All right. Okay. So here, what is our? Is my screen visible?
Yes, sir.
Okay. So our first given a list of the arrays is this one. So 2, 9, 7, 6, 5, and 8, right? So these are the list of the keys, right? List of keys are given for us. Now our first step is construct tree for this one. Okay, construct a tree for this one. Which screen you are seeing? Kindly respond, please. So the heap and the keys has been underlined with the red finger. The same screen you are seeing. Can you respond, please? No response. Can you respond, please? Which screen you are seeing?
Heap, sir.
Heap, right? So yes, the same which I am writing here. Is it visible, right, for you? Okay. So the
Yes,
first
sir.
step is construct a tree for this given list of keys. Construct a tree for this given list of trees. I told we will construct the tree from the root node. Okay. So root node, the first node is 2. Next, this node I should give, right? Which is this node 9. Next, right node, which is this node
7.
7. Next, left for 9, which is that next key we are having 6.
6.
So next key we are having 5.
5.
So next we are having 8, right? So this is a binary tree we wrote now. Okay, the first step is construct tree for the given list of keys. Okay, now you check for the parental dominance of this one. You check for parental dominance of this one. Parental dominance means the root node should be greater than the child node, right? The condition, the root node should be greater than the child node. Okay, and that you should check from the last node, that is parental dominance. You should check from the last node. Here the last node, which is the last node we are having?
8.
So the last node is 8, right? The last node is 8. So from this node, you should check for the parental dominance. So here, you can just compare here. 8 is greater than the 7, but 8 is at the leaf node. So what we should do? We should exchange these two. Okay? So here, since the parental dominance, what is the reason? The parental dominance does not hold, right? So here the parental dominance is not holding. So exchange 7 and 8. Okay. Since here the parental dominance does not hold, exchange 7 and 8. So if I exchange, what will be the tree? True will be here, and here 9, and here. So if I exchange, what will be the root node here? 8.
8.
So here it is 6, and here it is 5, and here it is 7. Okay, 7 and 8 has been exchanged. Now similarly, you check for the parental dominance. Is it holding here? Is it holding? See here, for this next node is 5. So this node is finished. Next node is 5. Is it holding?
Yes, sir.
Next node is 6. Is it holding?
Yes, sir. So
Okay. So this level is finished. Next is what?
9 to 8, 9 to 2.
right? So here next node is 8, right? Next node is 8, right? Are you getting? Are you getting here? Just observe here. So the parental dominance for the node 9 holds good from 5 as well as from 6. So no change. Next we will go for next node. Here we are having 8, right? Does it holds 2 and 8?
No, sir.
No, sir.
It is not holding, right? You just observe here. For 2 it is 8 and it is 9, right? For 2 it is 8 and it is 9. Does it holding the parental dominance? No. So no means what we will do? What we will do?
Exchange.
Right? So here the parental dominance, here it is not holding. Similarly here also it is not holding, right? Here it is not holding. Similarly here also it is not holding. So what we will do? So this tree we are checking for. Okay. So let me erase this. This tree we are checking this and this, right? So here it is holding good. So here you just write the parental dominance for node 9 holds good. Okay. So the parental dominance for 9 holds good, right? So here from this side as well as from this side, so it holds good. So what we will do? We will just write as it is 2, so 9, and here it is 8, and here it is 6, here it is 5, and here it is 7. Now you check for the parental dominance for 2. Okay. Now you check for parental dominance for 2. So it is not holding good, right? So here what we will write? So here what we will write? The parental dominance does not hold good for 2, right? For 2 it is not holding good. So exchange 2 with its largest key children, right? Which is that?
9.
9.
So 2 and 9. So exchange 2 with its largest key children, 9. So when we exchange, what we will get? Okay, is this? Okay, so when we exchange, what we will get? Which tree we will get here? When I exchange, so here 9 will be there, and here 2 will be there, here 8 will be there. Similarly, here 6, here 5, and here 7, right? Now, so now it is finished. Again, you check this tree. So here it is not holding. Again, it is not holding here, right? Again, it is not holding good here. Is it not? Can you respond, please?
Yes, sir.
Yes.
So again
Yes, sir.
the parental dominance for 2 does not hold. So here you wait. The parental dominance for 2 does not hold good. So you exchange 2 with its highest key. So here we are checking for this one and this one. So what when we exchange? So which one we should exchange here? Which one we
6.
should
6
exchange?
and 2.
So 6 should come for root node. So here this will give. So 9 will be as it is. So here 2 will be exchanged with 6 because in this in this one in this one 6 is the highest value we are having. So hence we are making it as root node. So here it is 2, here it is 5 as it is. So here it is 8 and here it is 7. Now you just check for this tree whether it holds good.
Yes, sir.
Okay. So now it is good, right? So it is the answer we are having. So this is with respect to bottom up approach. Okay. This is with respect to bottom up approach. Kindly remember, in bottom-up approach, first we will construct the tree, then we will go for heapifying. Okay, heapifying is that is checking the parental dominance of the keys. If the root node is less than its children, then we will keep on exchanging. So this procedure we will call it as heapifying. Is it clear? So in bottom-up approach, first we will construct the tree, then we will go for heapifying operation. Is this clear? Can you respond please?
Yes, sir.
So always here one point you should keep it in mind. Always we should check from the last leaf node. Always we should check from the last leaf node. See here we checked with 8 and 7. Next we checked with next values 5, 6, 9. Next we checked for the root node. Okay. Always you should start from the last child node. Okay. So please remember, since we are having two approaches in bottom up approach, first you construct the tree, then you go for heapifying operation. Okay. Is it clear? You just observe here, right? And now we will just go through with this clearly. Now you will understand these points very clearly. First, it initializes essentially complete binary tree with n nodes. Initializes the essentially complete binary tree with n nodes by placing keys in the order given and then heapifies. By placing the keys in the given order, then heapifies the tree as follows. That is what we followed here. First we constructed the tree, then we gone for heapifying. Is it clear? That is the first thing we should follow in bottom-up heap construction. Okay, what is this says? Starting with last parental node and ending with the root, the algorithm checks whether the parental dominance holds good for the key at this node. If it does not, then the algorithm exchanges the node's key k with the larger key of its children, and checks whether the parental dominance holds for k in a new position, and checks for parental dominance holds for k in new position. That is what happened with respect to this 2 here. It is not holding. So what we did? Again we exchange. So we should repeat this procedure. Right? So after completing the heapification of the subtree rooted at the current parental node, the algorithm proceeds to do the same with the node's immediate predecessor. Okay, so once it is finished, the algorithm stop after this is done for the tree's root node. I hope you understood now, right? So first we will construct the binary tree, then we will go for a heapification procedure. So this will continue unless until the entire tree will not, sorry, the entire tree will hold good for the parental dominance. Is it clear? Is it clear? Kindly respond, please.
Yes, sir.
Okay. Now I will just to go through with this one with algorithm with this algorithm. So algorithm for heap bottom up approach, right? So the input an array of keys is given. An array of keys are given, right? So for I is equals to n by 2. Why it is n by 2? Why it is n by 2? Because I told if an array is given, the first n by 2 will hold parent nodes or the root nodes, and the last n by 2 will hold child nodes, right? So that is what for I is equals to n by 2 to 1. So we will keep on constructing. Okay, we will keep on constructing the tree. Next we are checking if while not a heap, while it is not a heap, then we will exchange. Okay, while it is not a heap, but then we will exchange. Okay, so I will give one more problem for you. Now we just try to solve that one. Okay, so construct heap tree by using bottom up approach. So for this one. Okay, so construct heap tree, heap by bottom up approach. Just try to construct for this one.
Done, sir.
Yes, finish that.
Yes, sir.
Okay. So we'll give some time to let the others also finish. Everyone finished that?
Yes, sir.
Okay. So what is our first step says? First step says construct a tree for this one with in the given order. So if I construct, we'll get like this, right? So 3, and here it is 9, and here it is 8, here it is 10, here it is 15, and here it is 12. Right? So this is a graph given for us. Now we should check for the parental dominance from the last node. Right? We should check for the parental dominance from the last node. So last node is 12. Right? So here we will check for the parental dominance. Right? So here, does it holds good for this 9? So it is 12, and here it is 15. No, it will not hold good for this 9. So exchange this 9 with its large key value. So here compared to this 15 and 12, 15 is a large key value. So we'll exchange this 9 and a 15. So when I exchange that, we'll get like this. So 3, and here it is 8. So here it is 10. And here when I exchange, I will get 15 here. And here it is 9. Here it is 12. Right. So it holds good for 15. Now you just check for 3. Does it holds good for 3? Does it holds good for 3? So here it is 10, here it is 8, and here it is 3. So the largest is 10. So exchange these two. So when we exchange, we will get 1 here, and here 10 we will get. Here 8 will be there, and here 3, and this side 15, and this side 9, this side 12. Now you check for this one, right? Now we will check for this one. So it holds good for 10, it holds good for 15. Next we will check for 1, right? Does it holds good? No, right? So here 10, 15. So 15 is a largest key value. So exchange these two. So when we exchange, what we'll get? We'll get 15. We'll get 15, and here 10 will be there, and here 1. So similarly, for 10 we are having 8, and here it is 3, and here it is 9, and here it is 12. So it does not hold good for this one now, right? The new position of this is here. So again here it does not hold good, right? So here it does not hold good. So exchange this. So when we exchange, 15 is here, and here it is 10, and here it is. So 9 and 12. So here it is 12, here it is 12, and here it is 9, here it is 1, here it is 8, and here it is 3. Now, does it hold good for all the nodes?
Yes, sir.
Yes. So this is the answer, right? Kindly check everyone got the same answer. Everyone got the same answer?
Yes, sir.
Yes, sir.
Okay. So this is how we'll construct the heap tree by using the bottom-up approach. Okay. I will give one more problem. So kindly construct. Okay. Heap tree for this key list, that is 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay. 10, 11, 12, 13, 14, 15, 16, 17, 18. So you kindly construct a heap tree for this one. Okay. The next approach, that is top-down approach, we'll discuss in the next class. Okay. I hope there is no doubt in this particular class. Is there any doubt? Is there any doubt?
No, sir.
Okay. Then, shall we wind up the session?
Excuse me, sir.
Yes.